Okay, hello everybody. Today we're going to talk about another kind of error correction code called low density parity check codes. So these are used very, very commonly today. All sorts of typically long distance communications use these codes. For instance, satellites. DVB is a standard for digital video broadcast. It's how you get TV. They use it in their latest standards. I think the Ethernet standard has started using it, although it's wrapped. It's like the inner code for an outer wrapping of read Solomon or something like that. So these are very, very commonly used. And interestingly enough, these were first described in the 1960s by this guy called Gallagher at MIT. And for 30 years, nobody really paid attention to them. It was a PhD thesis. Then in the 90s, people looked at these codes again and realized that they had some very, very interesting properties that were useful and came up with better algorithms to use these codes. Right. So what are we going to go over today? I think last time you guys probably covered Hamming with Sam, right? So Hamming codes are great, but a large part of this presentation is going to be sort of formalizing what does it even mean? What does an error even mean? What does it even mean to send a message, right? And also, what does it mean to have a code? What are error correction codes trying to achieve? And then, so in the first part, we're also going to talk about how do you evaluate the performance of an error correction code, right? So let's say you come up with Hamming, and then I want to use that. Someone else wants to read Solomon. How do we decide which is the right one? Where you want to read it? Yeah. Dude, Zoom is a massive pain. Okay. All right. So after that, we'll talk about how to decode some simple codes that we described. There's this thing called soft decoding, which is interesting because you guys talked about the decoding we talked about for Hamming is actually hard decoding, and we talk about what soft and hard mean and why soft decoding is kind of more interesting. Then we formalize this thing called a linear block code, right? So what does it mean for it to be linear? What does it mean for it to have blocks? We'll talk about that. And LDPC, this last topic over here, sort of combines everything into, one interesting error correction code. So questions so far about what we're going to do? Okay, so here's the model, right? This is Shannon's model for what it means to, transmit information. So this is the information source. Let's say it's you typing into your keyboard, right? Then there's a transmitter. So this is actually a couple of things here. Is typically the way we're going to look at it is that it's a modulator, right? And what a modulator is it takes in a bunch of bits and turns it into a signal, right? So a signal is a function that varies with time, right? So on the x-axis you'll have time, and the signal goes up and down. So like sine of t is just a simple sinusoid, right? That moves forward in time. Which is great, right? So you send your signal out here. There's some noise source that adds noise to the signal or changes the signal somehow, right? So maybe a really easy way to add noise is just to add a constant every time. Okay, it's also easy to correct for, but that's one form of noise. It's just a shift. Anyway, at some point you receive the signal. This thing, the demodulator, so it takes in a signal, spits out the bits it corresponds to, and it reaches the destination. So what we simplified into modulator and demodulator here, you can sort of enhance this by before you do your modulation, i.e. before you turn your bits into a signal, you apply some sort of code to it, right? So maybe you add parity bits like in Hamming or something else, right? So typically this involves adding bits to add redundancy. And on the receiver end, after you do the demodulation or during or somewhere in that process, you reverse this code to figure out, well, what was the actual message, and if there are any errors, you correct them. So does the model make sense overall? Cool. Great. So let's talk a little bit about modulation, right? This is a little bit of like analog signal processing stuff. But the reason we talk about this is because once you're able to at least nominally understand this, there's a very, very simple model mathematically of this of all of the signal processing math that is just really, really simple, and it makes all of our analysis much easier. right? So we will use this thing called binary phase shift gain, which basically the main idea is you have some sort of basis function and some sort of sinusoid, right? To send a 1, you change the phase to something, and to send a 0, you change the phase to something else. So I'll show you what this looks like in the time domain in a second. And it looks hard, obviously. But the really important part is these two quantities. So S0 is the signal that you use to represent the 0 bit. That's some sinusoid with some amplitude, whatever, right? But it has a phase of plus pi over 2, right? And for 1, use a phase of minus pi over 2. So the difference in phase is 180 degrees. Makes sense? And this is sort of hard, but this helps, right? So this is a phasor diagram. It's also called a constellation chart when you're doing modulation stuff. How many people are familiar with phasors, I guess? Okay, so I guess just kind of as phasors is not useful. So in a sense, the idea here is this is another way on the complex plane to represent the same signals we were talking about earlier. So there's Euler's identity to convert sinusoids to powers of E, right? So what this is the distance from the origin to this point is the amplitude of that signal we saw earlier, right? And the angle, basically the argument of this complex number, gives me the actual phase, right? So here, if you look at the difference in phase between these two representations, that's the 180 degrees I was talking about. So the key takeaway here is this image is actually reversed. You just choose one way. So the way we like to do it is we map 0 to +1 and 1 to -1. Does that make sense? So it's just flip from the image. But the key point here is that we're mapping something in GF2 to a real number. Does this make sense? So to encode the bits, you don't really need to understand the signal processing, but what you really need to understand is 0 maps to 1 and 1 maps to -1. So we're creating some sort of mapping from our bits to real numbers. Make sense? This is what BPSK actually looks like in the time domain, and the reason this is useful to know is because these are actually the signals you're working with, right? So this is like the carrier wave. This is just the basis function for the signal. This is your bit stream, right? So you have 1 0 1 0 0 1 0 1, right? And if you look at these points of interest, like the vertical lines there, that's where the phase is changing. So you can see the signal changing its phase at those points. So that's really how your information is getting sent. Does this make sense? Cool. And the reason it's 180 degrees is that's just a way to describe whether those two signals are sort of in sync or out of sync. And 180 is the most out of sync that they can be. Makes sense? And the reason you want them to be very out of sync is because this makes 0 and 1 as different as possible. Makes sense? So that there's less of a chance that a 0 becomes a 1 or a 1 becomes a 0. Right? So we're already trying with our modulation scheme to correct this. Okay, so now we did the modulator, right? So we went from bits to signals, great. But what we still need to do is add in our noise. And a very, very useful model of the noise is this thing called AWGN, which stands for additive white Gaussian noise, right? And it's a very simple description. NT there is the noise. Fundamentally, NT is a Gaussian process, right? So they're like the normal distribution, also call it bell curve. So that's how you model, the noise. The reason it's called additive is because this is an addition symbol, so the noise gets added on, right? White is interesting. White means that from bit to bit, your normal distributions are independent. Okay. And that's just a property of the distribution, which basically says if there's an error, if there's noise that affects some bit, no matter what that noise looks like, there's a completely new, identical, independent distribution for the next bit. Makes sense? So sort of what this is sort of saying is that it basically doesn't model burst errors or anything. Right? It's just all of the bits sort of independently feel noise. Makes sense? In your channel. So there's a model of a channel, right? And this isn't the only model, and binary phase shift isn't the only way to modulate. But this is a very, very useful model because there's a very simple description of it. Let's talk about demodulation before we simplify this whole thing. This looks really, really bad, but really all this is saying is it's doing a little bit of analog signal processing. So all it's doing is it takes the signal you get on the input of the demodulator, multiplies that again by the basis function, the carrier frequency, and the carrier sinusoid, And after that, it basically is able to extract a real number, right? So why this works is not particularly important, right? I mean, basically, what happens when you multiply that signal back is you get like two really high frequency components, double the frequency, and the data is left like in the middle of the frequency domain. So you just have to look at it. All of this is not relevant. The really relevant point is the output of your demodulator is a real number. Does this make sense? Why is it a real number? It may not be exactly -1 or +1 because the noise is going to shift those real numbers around a little bit. Does this make sense? So let's say I send Anakin a +1, he might receive with, whatever statistical probability the Gaussian gives, maybe 1.3. Make sense? And it might go the other way, right? So the probability of a +1 turning into a -1 is pretty low still, right? Assuming that your Gaussian has some variance. But we should talk more about what that probability is, right? But the key takeaway here is that your demodulator output is not binary. It's a real number. Does this make sense? So typically demodulators are analog and they have to make some decision as to how to turn this real number back into the discrete values that we started with. Yeah. Another interesting point here is they don't have to map those to -1 and +1. The output of your demodulator could very well be a fixed point number that is then used by your error correction scheme, right? By your decoder. So more thoughts, but anyway, we need to somehow decide what this real number maps to. So we, in a sense, we're reversing that mapping where we mapped zeros and ones to real numbers back from real numbers to zeros and ones, right? So this is a really, really obvious thing to do. And this is where that hard decision, soft decision I was talking about comes in. And what's really obvious is a threshold at 0, right? So if you remember that constellation diagram, what we had was something like this, right? So you had +1, wow, that's bad, and -1, right? So you say anything to the right of this, I will map to +1, anything to the left of this, I'll map to -1. And that's a really easy way to threshold. Does this make sense? And that's the piecewise function that represents them. And we'll talk about soft decision decoding soon. Okay. So this is a really simple model of all the math we talked about earlier. But the reason you should know about the math is because you can actually derive this from them. And this is the model, right? So this is called a BSC, a binary symmetric channel. And there are various kinds of channels. There's another one called the binary erasure channel, where 0 can become 1, 0 can stay 0, or 0 can just get erased to a third state there. That's a 3 array channel sort of. But we use this because, if you think about it carefully, BPSK over AWGN is exactly this, right? Because you have a probability that it will flip, you have a probability it won't flip. But there's never going to be a case in this modulation demodulation scheme where something's going to disappear. Does this make sense? So there's a binary symmetric channel with transition probability P. So this is, you can think of this as like a Markov process, whatever you really want to do. Okay. Questions so far? Okay. So very interesting one to compute is the bit error rate P, right? Which is, you can think of it as a rate, you can think of it as a probability, same thing, right? So this is the probability that your bit was a 0 multiplied by the probability that that output is less than -1. So that's or equal to, right? So that's going to decode that thing or the other thing. So we assume that there's like an even mix of zeros and ones, and this probability is given by like the Gaussian, of course. And this is the bell curve I was talking about, and eventually it just boils down to like that really simple thing after all. It's not really relevant with the calculations. It's very, very manual and not interesting. This is the complement of the Gaussian error function. It's 1 minus TRF, right? So the big thing to understand here is that the bit error rate is somehow dependent on the variance of your additive white box signals. Make sense? So if you increase the variance, what's going to happen? Yeah, the error rate will go up. Yeah. Right. So you won't be, ideally you want to minimize this. Here's this other thing called the signal to noise ratio, and we discussed bit error rate and signal to noise ratio together, as you'll see in a second for a useful reason. Signal to noise ratio just says how powerful is my signal relative to my noise. So it's sort of like saying if you're in a noisy room, if I whisper, you won't hear me, but if I scream really loudly, right? So it's the same idea. That's also a signal to noise ratio. We usually measure this in decibels and stuff like that. Not super relevant, it's just logarithmic scale. But the interesting part of this computation is ES is the energy you use per symbol that you're transmitting. Right here, it's just the energy of a bit. And N0/2 is this thing called like the power spectral density. It doesn't really matter what that is. It's really just the variance, or I guess, yeah, it's just the variance of the noise. Does this make sense? So your SNR is really just that. And you might sometimes see these two formulae, but they're in terms of other stuff, right? So that's your signal to noise ratio, right? So as the variance of your noise goes up, your SNR is going to get worse. So there seems to be two sort of battling things here, which is the bit error rate and the SNR, right? It seems intuitive that if you increase the power of your signal relative to your noise, that is, you will get less errors. So we should formalize this equation, and we need a relation, right? So the energy per symbol is just computed like this. It's like whatever, it doesn't really matter. SNR is 1 over the variance, and you get this really, really nice and simple relation. And this is really what we were chasing, is this super simple relation between the bit error rate and the signal to noise ratio. Make sense? So what do we do with this graphic? Here's a Monte Carlo simulation that took a few hours to run. Can anybody think about why there are no? So the red line is the Monte Carlo simulation. Why is it that like it cuts off here? So the black line is just a plot of the thing we got earlier, but why does it sort of cut off here and we don't see any more of that other Monte Carlo simulation beyond the circle? To be clear, this axis is the SNR. This is a slightly different quantity that we'll talk about. Basically, it's a way of scaling the signal to noise ratio to adjust for certain constant factors. It doesn't matter. And this is the bit error rate. So I'll point out some relations. As your signal to noise ratio is going up, right? So when you're like near 12 decibels, your bit error rate is really low, right? I mean, you're getting like 1 in every 10 raised to 8 bits. I mean, really low, right? Whereas if your signal to noise ratio is low, something like near 0 or 1 dB, 1 in every 10 bits is off in our model, right? So this is bad, right? But back to my question, why is it that we're not actually seeing any of the Monte Carlo simulation down all the way down there? Yeah.
I think it's because there's only so many test instances of the Monte Carlo simulation. Anything below there is just, there's no errors.
Exactly, right? Because your signal noise ratio is so good, right? Your signal power is so much that you're just not seeing any errors, right? Because you're experimenting. Right? Monte Carlo is a random simulation. I'm just doing a bunch of trials, and down there I just don't see any errors, and it actually gets very, very hard to find, right? Okay, what's a disadvantage? So it's clear that oh yeah, if I want to, if I don't want errors, why do I need to do all this math that we're going to do and we've been doing? Why don't I just crank up my signal? You don't think about why that's not a good solution? Yeah, it's expensive. It's expensive, right? So imagine you're building the latest iPhone for Apple or Samsung or whatever company you like. If the antenna engineer and all the communications people come to you and say, oh, we want to crank up our signal power by some logarithmic factor here, you're going if you're the engineer, you're going to say, well, that's going to eat up battery too quick, right? So using more power is not typically a good solution. It works, and often it's the only thing you can do. But sometimes you can't, right? So for instance, let's say you're trying to broadcast messages into space, saying just use more power doesn't always solve the problem. So what does an error correction code do to this graph? What it does is it shifts, so this is the uncoded thing, it shifts it inwards, right? Which is to say, at the same power, let's say, right, you're getting a lower bit error rate, or at the same signal to noise ratio. So makes sense? So error correction codes sort of are able to take this and pull it inwards so that you're getting lower bit error rates without using more power. Well, with the additional power, of course, of doing the actual decoding and error correction code itself. But typically, this works out. Does this make sense? And this gives us a framework for evaluating error correction codes, right? So there's evaluating some sort of apologies. There's evaluating some sort of Hamming code, right? So as you can see, if your power is really low, in fact, it doesn't do that well, right? So you need some level of signal over the noise to even like transmit. But yeah, I mean, it helps, right? Over the uncoded just BPSK. Questions so far? Okay, nice. So quickly, I want to go formally into the Shannon limit. It's a bunch of information theory that's not super relevant, but it's interesting because it shows up in this graph in a very, very nice way. And it's just the furthest you can push a code. So your codes, by the way, look at so this is near 10. The previous graph I showed you is near 12 dB. So a nice relation to remember is that this graph starts at like 10 raised to -1, goes down to 12 dB, right? So sort of try to remember that curve if you can. And let me just quickly talk about this. This is a scaled version of the signal to noise ratio, right? So this is called the SNR per bit because some error correction codes use symbols that are made out of multiple bits. So it's not fair to compare them like that. You have to divide it by the bit, right? So that's all that saying is. It's just a fact. But yeah, so if you look at this, we're down here 10 raised to -1. Now, if you think about it, these are extremely good codes, right? Because we're getting like really low error rates just at like 4 or 5 decibels, right? And that's really the uncoded thing. So we've zoomed in a bit. And this is the Shannon limit. This is like the theoretical limit for a channel capacity, right? So that's the best rate you can meet, assuming whatever bit error rate you have. So for a certain bit error rate, you know, that's the best we get. Or sorry, for a certain second. But and a code of a certain rate, etc., etc., etc. But that's the limit, right? And the code we're going to discuss today is LDPSYM. That's from a class of codes called capacity approaching codes. So what that means is their lines are getting very, very close to the theoretical limit for how good our codes can get. Make sense? So let's talk about decoders. Decoders are really the interesting part of error correction because encoding, as you'll see quickly, is a pretty mechanical process. There are optimizations you can do, but fundamentally it's just a matrix vector multiplication. Yeah. Decoding is much, much more interesting because you have to come up with clever algorithms that fit power constraints, fit complexity constraints, etc., etc. And another wrinkle is that most of these are done in hardware. You will think about why that is.
Yes, that's an efficiency thing.
Efficiency, right? So if you start implementing these computations in software, they'll never finish. This is sort of if you think about like the OSI model or the network stack, you want to do this as close to the hardware as possible so it's fast and efficient. Right? So while we can make the math very, very complicated, there's still a lot of value in trying to make our operations as efficient as possible. And you'll see that LUPC is one of those codes that does do this, right? And the efficiency comes out of a lot of very, very clean math, which is why I wanted to show you guys this. Anyway, so what's the easiest way to make sure someone understands what you're saying? Repeat yourself, right? So repeating yourself twice isn't enough because now I don't know which one you meant, right? So you have to say it 3 times. Make sense? That's called an N is equal to 3 repetition code, and you do a majority function. So let's say I want to send you 0. Instead of sending you 0, I will send you 0, 0, 0. Let's say 1 bit gets corrupted, you get 0, 0, 1. A majority of those bits are still 0, so you know I meant 0. Make sense? That's a repetition code. Note that the rate of the code is 1/3, right? So there's 1 data bit for every 3 code bits. Make sense? So it's pretty low rate. But yeah, this is S, which is the actual signal, right? We're not writing the signals as BPSK anymore. We're just using, as promised, the map, right, between zeros and ones. I guess this is using the reverse. This should be +1 and -1, but you can pick up. It doesn't really matter where you map 0 and where you map 1, as long as they're off by 100 or 5. Okay, here's how to decode this, right? So I gave you an example, we decoded this very quickly. This is just a majority function, right? So first you hard decision decode that real vector you got. So let's say you shoving S into our channel, right? It accumulates a bunch of errors based on the Gaussian process, EWGN. And what you get out on the other end is these things with some errors, right? So maybe +1 becomes 1.2, maybe -1 becomes -0.5, it checks your improvement. And then you threshold it, like we talked about there, right? Make a hard decision, which is if it's above 0, map it to 1. If it's below 0, map it to -1. So split the plane into 2 halves. And after that, use a majority function, right? And what this means is this is like what you get R, which is the real vector on the demodulator set. Turned into B by thresholding, and then use a majority function on B. And C hat or C cap or whatever is the estimated code word for what you transmitted. So if you get more zeros than ones, you map it to 0. If you get more ones than zeros, you map it to 1. Does this code make sense? Questions about this code? Okay, how do you think this is going to perform? So I'm going to plot. Or well, there's some algebra that you can use to compute this. This is the same algebra you're doing earlier, right? So EB over N naught for this, you account for the rate here, right? And you get that for EB over N naught. And Q is actually the square root of this guy, right? So do that, or well, the signal noise ratio itself. And this is the probability of, so this is the probability of a single bit flip. But to actually create an error in our coding, the bit error rate is slightly different. It's this, right? So this represents the probability of 2 bits flipping, but 1 bit not flipping, or all 3 bits flipping. Makes sense? So that's the overall error rate. And turns out this does this, right? So we might as well not be coding because we've actually pushed this in the opposite direction that we intended to. So this is sort of illustrative, and it explains why we sort of need more thought in designing good codes. Does this make sense? Yeah.
Can you explain again why it does this?
Well, you can simulate it, or here's the calculation for that. So if you actually if you plot this, if you plug in this P into this bit error rate, and then plot that, you get this. So it's just a graph. Don't worry too much about like why that math comes about if you don't want to. But in general, repeating yourself 3 times is really efficient. That's sort of why. Okay. But yeah, repeating yourself 3 times means that if I want to send 1 bit, I'm sending 3 bits. If I want to send 1 megabyte, I'll be sending 3 megabytes. And that's just really bad. The only reason this even covers is it's actually able to correct errors if they happen. Right? Okay. Soft decision is much more interesting. Right? It is also called maximum likelihood decoding. And instead of doing this hard thresholding that we talked about there, don't do that. Right? Your real vector actually contains interesting information. Can anybody think about why that is? What information does thresholding cause me to lose that the real vector actually hadn't? It's about how close stuff is, right? So if you have some value like 0.01, how sure are you that that could be either? You're actually pretty sure it could be either, right? So what thresholding does is when stuff moves towards the origin, right, it makes a very, very strict decision, but it makes a strict decision in the sense that the strict decision says, oh, I'm very sure that that was a 0, that was a 1. But this is not necessarily true, right? You actually have less confidence in stuff that's closer to each other, closer to the origin, than stuff that's further away. And that's sort of the information you lose by doing thresholding. And we formalize this with some probability, but that's the idea. Anyway, so the idea of soft decision decoding is you analyze that real vector in a real vector space. So you basically compare the correlation with each covert, right? With covert, sorry. So you take the dot product, basically how similar is the vector to each one, and you use that to decide which one it is. And if you expand this out, the simplest thing you'll get is just check that the sum of the real numbers you get is greater than 0, and that's much better. Makes sense. And this is in fact the optimal decoding scheme for repetition codes. And turns out this does exactly as well as an uncoded sort of thing. So we've gone back and achieved what BPSK gave us. Yes. Yes, this is still the repetition code, right? So if you look at the code, what's this +1 +1 +1 +1. So yeah, this is still the repetition code. It's just instead of mapping it to bits and then using a majority function, you're just trying to figure out you're just trying to analyze the vector you get back in like a real vector space. So it's three-dimensional or whatever. It doesn't, compute on that. Makes sense. Okay. So yeah, we went back and achieved channel capacity. Let's sorry, we are not achieved channel capacity. We went back and achieved where BPSK was doing. Hey, does everyone remember the Hamming code? Hope you remember this. I think Anakin also covered this at some point. But yeah, the big idea here is your data bits are D1, D2, D3, D4, and your parity check bits, P1 takes the XOR of D1, D2, and D4, P2 takes the XOR of D1, D3, and D4, and P3 takes the XOR of these three bits. Makes sense? There's a cute Venn diagram that represents it. So the reason this works is I think Sam might have talked about this. You basically get some nice results from these big powers of 2, right? And eventually you're sort of able to binary search to the exact transfer. Anyway, so how do you do hard decision decoding of Hamming? You guys know this. It's basically do thresholding, get the actual vector, and then compare Hamming distances with code words, right? So I think Sam talked a little bit about distances in codes, right? So how with the minimum distance between two code words and how you correct for that. So you just correct to the code word that's at the closest Hamming distance. Makes sense so far. Cool. So this is the minimum distance decoder, right? This just finds the code word that's the closest in terms of Hamming distance to your thresholded receive vector B. There's also the soft decision decoder, and this works in almost exactly the same ways. You find the closest code word in Euclidean distance, right? And this is the soft decision in whatever r raised to n, where that's that's Rn. So what you're doing is the code space is a subspace of that entire vector space. So you're just trying to bring it to the closest point in the code space. Makes sense. And obviously this is much more complex, right? So going back to trying to implement some hardware or something, computing this stuff is not hard, right? Because you have to sort of the most naive sort of implementation of this is compute the Euclidean distance of your received vector with every possible code word and then find the value. Right? So there are obviously much better ways to do this. But again, this is like more complicated and it becomes hard to implement as you get like larger and larger real spaces, right? With longer and longer networks. So this stops making sense to do something. But this is the maximum likelihood decoder for that. And as you'll see, the maximum likelihood decoder actually does really well. Yeah. So uncoded is the black line. Hard decision only starts to do well at higher SNRs, but if you really want Hamming to do well, you need to do a process that's closer to maximum, at least for the 740. Okay. The last kind of decoding we'll talk about, and this is really the meat of what we're going to talk about today, is soft in, soft out decoding. So it's called CSAT. And we start by implementing for the repetition code because it's easy to do so. And we're not really going to try to analyze how this does independently using the graphs. These are ingredients, the CSAT decoders are ingredients in the LDDC decoder, right? So doing it for repetition codes is really easy. So going back to what I was talking about earlier with beliefs, right? So the output of this decoder is this real vector. So it takes in the real vector R, right? And it outputs another real vector L, where each of the elements of L represent the strength of the belief that like bit I is, let's say, 0, right? So what does this mean? It means that let's say you receive this vector here, 3.2, 4.3, 2.4. In each case, it's very likely that transference symbol was 1, right? Because going all the way from -1, jumping all the way here is very unlikely, right? But going from here to here is much more likely, and this is just because of how the Gaussian distribution works. Make sense? So with high probability, you know that all of these will pass. However, look at this, right? And now you're not so sure. A hard decision decoder would say, well, it's 1, -1, and -1, and that's because it's only using what we call intrinsic information. Right? So it's looking at this in a void without looking at its relation to the other things in the vector, and that's extrinsic information. Makes sense? So what soft and soft out decoding tries to do is it tries to use the relations between these guys, right, to combine the intrinsic and extrinsic information to get a better estimate. Makes sense? Or to tell you how strongly it believes that some bit is zero. Right? So you know for a fact that like all the bits should be same for repetition code, right? So if you think about it, actually doesn't make too much sense to look at it this way, especially since there's such a tiny value, right? Just by looking at it by intuition, you know this thing is a -1 and that accidentally crossed the threshold, right? But if you use a hard decision decoder, it's never going to be able to tell. So clearly we need to somehow make some sort of algorithm, some sort of system that's able to tell us how much it believes something is true. Okay, so this is Bayes' rule, pretty easy. This is the probability that C0 is 0. So C0 is like the code word you output, given some value of R0, right? So Bayes' rule is pretty simple. And how many of you are familiar with Bayes' rule? Okay, excellent. So I need to explain this, where we get this, where we get this. It's very natural to divide these quantities because they have the same denominator. And we assume that the probability of seeing a 0 and the probability of seeing a 1 is about the same. Right? So divide both these quantities, you get this, right? So this f over here is just like the normal distribution. Well, the conditional normal distribution. It's R0. It's a distribution of R0 given that C0 is 0. And the distribution of R0 given that C0 is 1. Right? And this still represents belief, it's just a ratio, right? And yeah, so we can prove this very quickly. Recall that the noise is normally distributed. So this distribution is actually just 1 plus whatever that is. The normal distribution with a mean of 0 and a variance of 6. Right? And this is -1 plus that. So plugging all of this into like the Gaussian probability distribution function, simplifying gives you this, right? So you can think about why that is, but lots of stuff cancels out. And eventually you just get this. And so we've computed the intrinsic log likelihood ratio of R0. And that's just the logarithm of this quantity, right? You get rid of that e raised to whatever. And we get this. So this is very, very general for any intrinsic log likelihood ratio, right? And why is this intrinsic? It's because the quantity we were computing is basically asking, what is the probability that C0 is 0 given R0? So we're looking at the same real number, the same index in the vector, to reason about the same index in the code, right? So this is intrinsic. This is like, this is in fact, when we were doing the sort of threshold hard decision decoding, we were ignoring this scaling factor and then just doing a map, right? So yeah, you can often ignore the constant factor since it's just a scale of your this is much more interesting, which is what is the belief in the context of the other elements in that, right? And this extrinsic log likelihood ratio varies depending on the kind of code that you use. Right? The intrinsic one is always the same because you always take a bit, map it to itself in linear block codes. But this extrinsic ratio is like much more interesting and harder to do. So the quantity of interest is this guy, it's the logarithm of the probability that Ci is 0, given that entire vector, right? So in the context of the entire vector. And yeah, skipping all of this transformation, like you're familiar with how this transformation happened. There's a joint probability distribution of these three guys. Remember what we said though, was that at a point Gaussian noise, the distribution for each of the bit errors is independent, which means the joint distribution is just a product, right? And after you insert the product of those distributions in the same case, you get this, which should make sense, right? Intuitively also, but you can work through the algebra, it's not bad at all. And therefore, the likelihood ratio, this is actually this is combined intrinsic and extrinsic, because for each bit I, we're looking at the entire vector. So it includes both the intrinsic and extrinsic components. And you can see that component here, the intrinsic component here, which is that one, and the extrinsic component is that one multiplied by the scale factor. Right? So doing soft and softer decoding for a repetition code just looks like this, right? So after adjusting for scaling factors, it's really just that, right? So for L0, let's say, it's just going to be the intrinsic plus those. And what it's really saying is, what do R1 and R2 tell me about R0? Right? Sorry. And in our example, where we had 0.02, this and this would result in this, which is much better, if you think about it. Because we're contextualizing each bit in terms of what the code did to the other bits. Makes sense? This is called a soft and softer decoder. This is great. Another interesting soft and softer decoder is that for single parity check codes. So single parity check codes are sort of a degenerate case, I guess, if you look at it. Of I guess Hamming codes. Really, all it is or a set that Hamming codes. Where you XOR all of the bits together. A single parity check is that. So you have some code word, right? Some message word, sorry, and you XOR all of its bits together, so you get one parity. Then you just pop that on. That's a single parity check code. And alone, it doesn't do much, but it is a valid code, right? And the reason it's interesting to analyze is because it tells us what the XOR operation on bits looks like in the log likelihood domain. Makes sense? So earlier we had the very simple operation of duplication of bits. That looks like addition in the log likelihood. So the question is, what does XOR look like? Makes sense? So look at the 3,2 single parity check code. So all this means is, are you guys familiar with systematic and non-systematic codes? Okay. So in a systematic code, what happens is you have these message bits. You can see the message in the code word. So usually it's like the first part of the code word. So in the code word, the message bits are separate and the check bits are separate. That's a systematic code. So this is an example of a systematic code where you have these zeros and these zeros here. And this column here is the parity check. And as you can see, that's just the truth table for X. Cool. So let's try to design a soft and softer decoder. Now I warn you, this is a little painful mathematically, but we can still do it. So we already know what the intrinsic thing is, right? It's just the same for all BPSK. But what do R1 and R2 say about C0, right? That's the real question. So what we want is the extrinsic likelihood ratio of L0. Let's see, that's what that represents. And that's the probability that C0 is 0 given some R1 and R2. Makes sense? Divided by the probability it's 1 given some R2, right? So this is really the extrinsic information. And remember, what is the relation between C0, C1, and C2? It's this, right? C0 is the XOR of C1 and C2. And this is how the XOR operation works. If you guys might see this as well, C2 is the XOR of C0 and C1, but it just you can change the equation like that. So you can prove to yourself that's true by the way proof table. But anyway, so the probability that C0 is 0 given R1 and R2 is what? Either if this is 0, that means C1 and C2 are both 1 or they were both 0. This is how XOR works, right? So that means where P2 is like this log, like this intrinsic log likelihood ratio, right? So you multiply those out where that's the probability that it's 0, that's the probability that there's a probability they're both 0, there's a probability they're both 4, right? And this captures sort of this information. You can do the same thing for the denominator, trying through a bunch of algebra. It's not very interesting. But this is the relation in the likelihood domain, is you get these hyperbolic time functions, which is itself composed of powers of p. Why does this happen? Reasons. It's just you're not even plugging in the Gaussian yet. Actually, what happens is since these themselves are logs, once you divide this and this, you get stuff that looks like 1 minus p1 over 1 minus p1. And when and it ends up looking a lot like the hyperbolic. So you pick this up. We still need to take the logarithm though. And breaking this up into like the sine and absolute values with logarithms, you get this, right? So the sign is really easy, it's just the product of the signs of L1 and L2. Then you get this function, okay, where this multiplication becomes addition in logarithms, and you get this. So if this looks bad, that's because it is, right? I mean, we were talking about, oh, we want our hardware complexity to be low. And obviously computing logarithms and hyperbolic tangents in hardware is not so good. But there's a very, very elegant approximation of this, right? To approximate this. And the way we do that is the following. I just want you guys to note this function is its own inverse. Okay? Which is an interesting property, but nonetheless, writing f as that function, you just get that, which is great. But if you notice, it looks like f is iterated over here, right? So it's interesting, and the reason it's iterated is because we took the one on this, we applied the inverse function to both sides of this f, right? And that's why we got this ICD. Makes sense? And here's like, I guess, the theoretical final bit is the overall likelihood is the intrinsic plus the extrinsic, right? The intrinsic is whatever the usual is for the channel. The extrinsic is given by the formula we computed earlier, where f of x is given by this log hyperbolic tan. Makes sense? And this is true for XORs. Makes sense? So even a simple operation like XOR, and the reason XOR is so important is because all parity checks are XORs, right? So this is a very, very important sort of translation into the log likelihood. Anyway, this is what this f of x function looks like. So can you tell me how you think about approximating this? I mean, this is a non-linear function. It's not a trivial function, but how do you approximate this? Yes. 1/x is an okay approximation, but you could do slightly better if you really know it. And the answer is, if you think about it, if you plug in any value, right, lower values tend to have higher outputs, and higher value as inputs tend to have pretty low outputs. So what we're plugging in, remember, is a sum of two things. So the output of this would be dominated by, or well, this result over here is going to be dominated by the smaller of L1, because that will have a larger output. Makes sense? So this quantity is dominated by the minimum of those. And the interesting thing is now we can use that iteration of f, right? So once I replace this with the minimum of these two, just because of the shape of this function near zero, what I'm able to get is it's the f function iterated twice, but it's its own inverse, right? So I just get the min of L1. And this is really nice because we converted all of our really complicated math back into a really, really simple approximation. And doing a minimum in hardware is just a comparison. So that's how the math gets complicated and then simplifies back down. But fundamentally, you just add on the minimum of these two guys and multiply by this that you computed. Cool. So this generalizes naturally to n minus one parity code. It's this induction, right? Same thing as, oh, I did one XOR in the log likelihood domain, so n XORs becomes this thing. So it's the product of all of these signs times the min of all of the other intrinsic log likelihood ratios. Makes sense? So again, there are low-hanging optimizations here for the sign that you can pre-compute it and then keep multiplying the new one. And the minimum operation, this output is actually always going to be the same, except when you're trying to compute the extrinsic value for the minimum one, where it will be like the second smallest value of that. Right? So this is really easy to optimize, but it doesn't really matter. Yeah. Yes, we're almost done. Okay, so I'm going to try to skip over this very, very quickly. We have 10 minutes, right? Okay, cool. So a linear block code takes this input vector, produces C, and this definition you'll probably go over again when you do like algebraic block codes. But fundamentally, the way a linear block code works, it takes some vector of its n, produces this output C, which is this is systematic, right? So it produces M again with a bunch of parity check bits stacked. So single parity check codes, for instance, are linear block codes as elements, right? So the elements appear to be by XORing or adding modulo 2 certain bits of n, right? So here's the 6-3 linear block code, right? So this is really easy. Each parity bit is computed by XORing. So you get your message bits are M0, M1, M2. So you XOR them in this fashion. And the rate is clearly 1/2 because 3/6, like K. Okay, slight formalization here is this thing called the generator matrix. Okay, and this is important because you take the message bits and how many of you know how to do this one? Okay, cool. So it should be pretty clear how this translates to this adding module when you do your math. Right? And you get the full systematic code word. All you do is you add on this identity matrix here, make sure you get those m bits there. And this thing here is like the parity matrix. Makes sense? So the general form of a generator matrix for linear block codes is some identity matrix whose dimension is the length of your message bits with concatenated with some sort of matrix that generates your parity bits. And you can wrap up having this way, you can wrap up almost anything this way. There's another thing called the parity check matrix, which is also important. What this says is if you do h times like the transpose of any code word vector, right? You just get 0 there. And this is a really good way of checking if the vector you receive is a code word or not. And if the product of your parity check matrix and your received vector is non-zero, that's called the syndrome, and that tells you that you have to do something. Make sense? So zeros here mean that you actually have a code word, and this is the form of the parity check matrix. So there's still an identity here, and this is the transpose of that parity check matrix. And you can verify for yourself that if you multiply G and H, you get 0. This is something you can do later, generate these matrices for the repetition code, because that's what's good. Okay. Ends up looking like this. It should be pretty obvious why this looks like this. This you can verify for yourself. Okay. Okay. LDPC. So we have all the elements of what we need to make these codes. So let's just make it. LDPC codes are linear block codes, so you can describe them with that generator matrix, parity check matrix formulation. With some very, very sparse parity check matrix X, right? So that is to say the number of ones inside this matrix is a lot less than the number of zeros. Make sense? Okay, Tanner graphs. So this is where a little bit of graph theory comes in. Here's my parity check matrix. Oh no. Do they have it at 6 or no? Okay, let me go through this super quick. Okay? So this turns into this. Why? Because this row turns into like that check node, and you can turn this into a bipartite graph. And none of this is super interesting, except you want to do soft and soft out decoding on this. So fundamentally, the algorithm is you pass messages along this graph. So all the variable nodes pass messages, the check nodes pass messages back, and sort of by talking to each other, they get a better approximation. I'll post the slides. This is sort of how they talk to each other. And eventually, let me just play this GIF because this is how the decoding eventually ends up looking. Okay. So that is like the iterative process as it goes through the graph, removing errors. I guess we can wrap up there because we're very low on time.